Hello everyone, my name is Marcin Niestrój and I will give a talk about connecting Zephyr logging to the cloud over constrained channels. A few words about me. So I work in the embedded space for about 10 years. 4 years of that I spent on working on Zephyr projects, built about 5 Zephyr-based devices. My contributions to Zephyr are focused to networking stack with a bit of TCP, PPP, and modem drivers. And I'm working for Golioth, developing Golioth SDK, which adds more features to already awesome collection of capabilities that Zephyr has. And what we'll talk about today. First, we'll talk about the logging subsystem in Zephyr. Basic concept, what are the high-level components, features, and how does it support extensibility. We'll use Golioth SDK in order to send log messages to cloud and retrieve those logs using a dedicated tool called goliothctl. Briefly talk about Golioth, what services does it provide, and how we'll use logging, backend, and LightDB for today's talk. And we'll talk about CoAP and CBOR. Both are used in Golioth SDK. They help in efficiently connecting IoT devices to the cloud, in particular how they are used to send log messages to the cloud and how they can be retrieved later on. So most interesting things to learn from this talk is how to access Zephyr logs without physical access to internet connected device, and how do log messages look like when encoded into CBOR and sent over CoAP. So we'll look into binary, how it looks. A few words about the logging subsystem in Zephyr. So there are 2 types of macros. First one is just the log macro. It works pretty much as printf and printk functions. It supports formatting and it allows to add more arguments and format a string. And then there is the log hex dump, which is a dedicated macro in order to dump memory contents or the buffer contents. So the contents of the memory in the binary form are presented to the user. This is especially useful when debugging UART, SPI, or I2C bus and developing Zephyr drivers. The logging subsystem has 2 modes, immediate and deferred. Immediate mode it works very similar to printf and printk, so the logs are printed or processed synchronously, so the execution of the thread that produces the log is suspended, and the logs then is printed, for example, by the UART device. And there is the deferred mode. This is actually the default mode of logging, and this is where the real power of logging subsystem in Zephyr is. So it allows to quickly produce the quickly store the arguments passed to the log macros, and then those format strings or the binary data, they are processed in the dedicated logging thread, which is lower priority, and it just allows to continue execution and also allows to generate logs from interrupt context. There are log levels, and most of the subsystems allow to configure that over kconfig. And there are multiple backends supported by logging. And the most commonly used are the UART shell. Those work pretty much like the printf. So the information is on the console. The RTT is very useful when there is no dedicated UART interface, and the JTAG prop can be used in order to still retrieve logs from the logging subsystem. And then there is the remote Syslog, which uses UDP in order to transfer log messages to a remote host over the UDP over network. And one nice thing that we'll cover during this talk is the support of logging subsystem to filter messages per module and per backend. So here is the high-level flow of how the log messages are produced in Zephyr applications. So there are Zephyr, there are log modules, and there's already about 800 log modules registered in Zephyr, and those are various modules like the Bluetooth, networking, settings, flash, or application modules. All those messages generated by modules are then lent in logging core, and there is the dedicated logging thread that processes those messages and actually produces the strings, adds the timestamp and the severity and so on. And there are the backends. And today we will talk more about the Golioth logging backend, which is an implementation that allows to send log messages over the internet and then retrieve them on the development machine. Just a few words about Golioth. So Golioth is a cloud solution for constrained IoT devices. It supports MCU-friendly protocols like CoAP and MQTT. It's secure by design because it uses DTLS and TLS, depending whether the UDP or TCP transport is used. It allows to use either Json or CBOR, depending on the developer needs. And it implements, provides multiple services. So DFU is the most obvious one for IoT devices. Then there is logging and the LightDB, which we'll cover during this talk. And there is the LightDB stream useful for sending sensor data. So how does the Golioth logging looks like, and how are the log messages sent? So there's the Zephyr device, and Zephyr device uses CoAP post requests that have CBOR as payload, and those log messages are sent to cloud. They are stored there, and then we can, as a developer or when developing an application, cloud application, we can retrieve those logs and also get notified about new logs in real time. So there is a web UI interface in order to do that, and also a CLI application. So Golioth logging backend, it is all about sending log messages over the network. And before we continue into details how the log messages look like over the wire, let's first discuss what the log message really is. So the log message is, first of all, a text string, which provides most information, but the log message also contains important metadata, such as timestamp. So it's very important to know when the log message was produced, whether it was 30 days ago, 1 hour ago, or a few seconds ago. Then there is the severity of the log message, which defines how important the message is. And this allows us to filter messages by severity. And there is the module name that produced this log message. So we might be just interested in networking stack messages or the Bluetooth or the application. And then there is the message counter or drop counter. And this is also quite important because it gives us possibility to get a feedback whether some log messages were dropped and we won't be seeing them. So at least it gives us feedback whether we missed some information or not. So this can happen when a lot of log messages are produced. Here we'll talk about the possible output types of logging backends. So we can either have the log messages represented as text or as a dictionary. So text is very simple. So the log message just needs to be converted to string. So if there's an integer, it's converted to string. If it's a binary data, it's also converted to, for example, hex string. And it doesn't require specialized tool to read. So in case of UART backend, we usually just need a console, a program that connects over UART interface and serves as a console. We can easily read that. When we have a file, then we can just use a text editor and read the logs. And in case of dictionary output type, this is arguably more complex to implement, and it requires a specialized tool to understand the logs. So if the logs are in a binary form, it's no longer easy or no longer possible to view those logs using just a text editor or a terminal window. But dictionary output type is good fit for datagram because each message is actually a structure. So we can just put this whole structure into a datagram and send it over the network using UDP or CoAP. And nice thing is about the dictionary output type is that out-of-order delivery is not an issue in case of UDP because we can add information about the index of the message and then reorder it on the other hand. So for the dictionary type of log output, we need some way to represent the object that we want to store. So first thing that comes to mind is the Json. However, it's text-based, so it's not a good fit for constrained devices because it produces more bulk, uses the network bandwidth. But the good thing about it is that it is extensible, so it's easy to add more entries to the JSON structure. Another issue is that adding binary data to JSON, such as the memory contents, is not easy because we need to convert that to a string, usually using base64 encoding. And then we can come up with some custom binary protocols. So, for example, prepend the log messages with 4 bytes of timestamp. Or we can move to a standard solution like CBOR, which is binary based, but still extensible. It has similar data model as JSON, and it's strictly designed for Internet of Things. So it allows to pack data efficiently, and it is easy to implement on a constrained device. So it doesn't require much footprint, flash footprint, and RAM memory. So we already know what to send. So we want to send a text message and the metadata that is attached to log message. So timestamp, severity, and what's the source of this log message. And we know that we will efficiently pack it into CBOR. But here comes the question, how should we send it? So can either decide to use TCP, UDP, which are transport protocols, but it's a better idea to use the application protocol because it allows to multiplex multiple services in one connection. And that's very important because we want to save resources. So the 3 application protocols that we can briefly consider is the HTTP. However, it's text-based, so it adds a lot of overhead, and it's harder to produce because all the binary data needs to be converted to string. Then there's the MQTT. It's common solution for embedded devices, for IoT devices to use that protocol. It's binary-based and it packs data efficiently. And there is the CoAP. And CoAP is nice because it shares the same feature with HTTP, which is request response. So it's easy to operate. using request response model, but it's binary based. And another feature is that it works on top of UDP, which allows to use it in even more constrained devices than MQTT, because we don't need the TCP stack with all the retry logic and resending. So those are the OSI layers that are used for sending logs to Golioth backend. And we'll talk today mostly about the CoAP carrying CBOR payload, but there is the DTLS that provides security, and there's UDP, which means that we'll use datagrams. So let's see how the log messages look like over the wire, how they are sent over the network. So here we register an app module with debug logs, and debug is the minimal log severity that will be handled. And we just produce a warning message with a counter inside. So on the bottom, you can see how the CoAP packet looks like over the network. So it's already obvious that it's much shorter than what the usual HTTP request would be, including all the HTTP headers. And let's quickly go through how the CoAP packet looks like. So there's a version of the CoAP, and there's the type of the packet. So this is a non-confirmable packet, which means that we don't wait for confirmation from cloud that it was received. This means that packet can be dropped, but it also reduces the RAM usage because we don't need to observe the state of the packet. Then there is the post, so we are adding this to the cloud. Message ID and token are CoAP specific things. Next important thing is the Uri Path, and this is something that defines which Golioth backend, which Golioth service we will use, or like any service on the server that we are communicating with. And then there is the content format which we will use. So this will be CBOR. There is just 1 byte of boundary between header and payload, and then there is the CoAP payload, and this is encoded into CBOR. So let's take a look how the CBOR looks like. So on the right side, there is a JSON equivalent of the CBOR payload. So as you can see, there is a message, and there are 4 other metadata information. So there's the uptime in microseconds, module name, log level severity, and index of the message. So index allows us to define whether some message was dropped or not based on after comparing 2 subsequent log messages, and if the index is if the index difference is more than 1, then it means that we drop some messages. And here is how the log hexadecimal variant is handled. So first there's the UART shell output, so the counter hexdump and the binary data converted to hex string, and then there is the representation in CoAP and in CBOR. So the nice thing about CoAP and CBOR is that the binary data is encoded in place. So if we just want to dump 4 bytes, then it will be the CoAP packet will be 4 bytes larger. If we want to dump 1 kilobyte of data, then the CoAP packet will be 1 kilobyte larger. So we can easily calculate how much data our device will be sending to the cloud when dumping memory buffers. So we already know how the packets look like, and that they are pretty small over the internet connection. And let's look like how we can right now retrieve those packets and display. So here we produce a debug message with a counter. We can see from the output of URL that there is the timestamp, which is 6 hours, 49 minutes, 9 seconds. There's the debug log level severity. App module produced that, and it was in the main function. And the log message is debug info 4900. And then there is the output from Golioth CTL tool. And the Golioth CTL output is much more verbose, but it contains all the data, if not more. So there is the timestamp when the log message was actually retrieved by a cloud. Then there's the severity, module name, message itself. Then there is the device ID. And there is the metadata, including the function name, index number, and app name. Metadata is something that cloud doesn't process itself, but it allows to transport it and like display using Golioth CTL. And output from Golioth CTL might not be as user-friendly as URL. So here's a quick way how to handle that case. So Golioth CTL logs listen command allows to output everything in JSON. And we can use Linux pipe in order to transfer this, to pass this JSON structure to JQ utility. And using JQ, we can format the string in a similar way as it is formatted using URL. So here comes a question. If we send all the messages that are produced by Zephyr OS and all the components and applications, then it already uses a lot of network bandwidth. And in case of IoT devices, this is an issue, and we cannot afford that, at least in a deployment stage of the product. So here is where the logging filters and Golioth LightDB come handy. And this is how the Golioth LightDB looks like. So it's really just a simple database somewhere in the cloud, and it allows to store CBOR or JSON objects. And both the Zephyr device and the user or the cloud application can access this data. And for our sample purpose, we will just use this JSON as, and we store this JSON in our database. And there's just the logs structure, and it contains pairs of module and log severity. So in that case, we'll instruct Zephyr device to configure app module to use debug log messages. And from the device perspective, the LightDB, for the LightDB, we use CoAP observe call, and this means that all changes in the database and the LightDB are instantly passed to the device, so the device can in real time change its configuration, and all the contents can be downloaded as CBOR map or JSON structure. And then for our sample use case, we will just apply those severity per module using the log filter set, which is just a Zephyr API for logging subsystem. LightDB from user perspective, there is the Golioth CTL LightDB command, and we'll just use the set capability. So we'll, for NRF52 device, we'll set the app module to the logging level debug. And this is how it looks like on the shell. So the Golioth CTL LightDB set is issued. Then we can check the contents of the LightDB using LightDB get to be sure that we have modified the database correctly. And then we can run the Golioth CTL logs listen command with the JQ formatting. And this is the output of the messages that are produced in an infinite loop. And there are four log level severity. So there's info, debug, warn, and error. And let's say that we are not interested in debug and info messages. So let's configure the app module to just produce warning messages and error messages. So that's what we do with Golioth LightDB set. We make sure that that's the case with LightDB get. And then we start the Golioth CTL logs listen command once again and observe what messages are produced in the loop. So here we see that just the error and warning messages pop up. So why is logging over internet so cool? So logging framework is already built into Zephyr, and there are almost 800 modules that are utilizing that framework, which proves that it's very powerful and useful for debugging. And by utilizing logging framework, instead of adding new APIs to produce log messages, we don't need to modify the source code of Zephyr in order to still monitor what happens inside the OS. And same tool that is used for early development, which is like logging over UART or over RTT, can be used for devices that are early prototypes, they are in field testing, or for devices that are even deployed in the field. And the only thing that changes is just the transport. So instead of UART, we will use cloud as a middleman. And this gives us also more capabilities because the log messages are stored, so we can view the history of the log messages. And the logging over internet can be easily controllable, and the logs can be filtered using the logging filtering capabilities, and for example, some ancillary services such as Golioth LightDB. And there's still room for future improvements. So right now, CoAP packets are sent without any confirmation, and which has an advantage because this reduces the footprint of the code, and also it's easy on the RAM usage because the CoAP packets do not need to be tracked, but reliability of sending the packets and confirmation might be useful in some cases. Right now, each log entry is sent using one datagram. This might not be efficient when the log entries are very small. So in some cases, it might be a better idea to pack multiple log entries into a single datagram to save the network bandwidth. Another idea is to collect messages and then send them all at once. This would be especially useful when IoT device just connects every single hour with the cloud. So this is when we want to dump all the log messages. And then there's the configuration of collected send metadata that we would like to configure. So right now, all the metadata is sent, and it's not possible to disable the uptime or the severity. In some cases, it might be useful to disable those in order to further decrease the payload of the log message. And sending module ID instead of module name might be another optimization. So instead of string, we would send integers, and this would save us another few bytes of data. So here are a few useful links. So first one is the logging backend documentation. Then there is the Golioth. And then there is a link to the branch, the code that was used during this presentation in order to filter the messages and send them to the cloud. And there are links to the formal specifications of the CBOR and CoAP, which define how those technologies really work and what each byte means and what are the capabilities of those, and how can those be utilized by other services in Zephyr-based devices. So thank you for this talk. That's all from my side. Thanks for listening.